All right, so the next speaker is Niccolò Cribiori, who's going to tell us about deconstructing scale separation with weak gravity and anisotropies. Thank you.
Okay, so first of all, let me thank the organizers. It's my pleasure to be here. And I was asked to talk about scale separation and was hoping to have some recent results, like in this period, but it didn't work out. So we'll talk about some results from this year, beginning of this year, and also from the past 2 years, more or less, done in collaboration with several people from various places. And let me start by remembering that Swampland conjectures, as we know, are a window into quantum gravity. The very fact that this conjecture exists or can be formulated is a proof of concept that quantum gravity is mixing UV and IR. And typically what you do is that you test conjectures from top down, so from string theory, because this is basically the best understood framework in which to work. And this is an extremely important job, because indeed it's the only way we have at present to gain confidence in those conjectures. However, this is not what I'm going to do in the first part of this talk. So in the first part I will follow somehow a complementary approach, which is that I will use, or I will assume, certain conjectures to be true, so I will not question them at all. And then I will use them directly as tool to rule out certain properties. In particular, I will apply them to 4D and 5D supergravity, being agnostic about the possible UV completion of this theory, so to any possible supergravity. And I will show that you can say something about scale separation in ante de Sitter, and also with some minor modifications, so with some small additional assumptions, you can also say something for the Sitter, but I will just be brief on the Sitter. I will mostly talk about scale separation. And for this approach to make sense, of course, you have to use conjectures which are tested and checked. And for this reason, we used the weak gravity conjecture, the magnetic version of the weak gravity conjecture, which is a statement on the ultraviolet cutoff of effective field theories, which is one of the most tested conjectures indeed. In the second part, instead, I will follow this more common top-down approach, and I will review some construction of scale-separated ante de Sitter for vacua we did with many people here in the audience in type 2A supergravity. There are many features one could discuss about this construction. I will focus on one of them, mainly for reasons of time, which is the fact that you have to insist on the internal manifold to be non-isotropic. So you have to move away the ideal situation we usually study, in which the full manifold is isotropic. And then as a final question, maybe this can be a more general lesson, and okay, but I cannot say much more about this for the moment. So let me start from the first part, where I will use weak gravity conjecture to put constraints on scale separation. Actually, the very idea can be understood from a different and simpler setup, which has nothing to do with scale separation, but the very idea can be understood from just for d n equal to 1 supergravity with one vector multiplet. Now, in this model, you can do a simple deformation of the theory, still preserving supersymmetry of the action, but breaking it on the vacuum. This deformation is known as Fayet-Iliopoulos deformation. It means you introduce a parameter psi, which is called Fayet-Iliopoulos parameter, which is generating a scalar potential. In this case, there are no scalar fields, so the scalar potential is just a constant. Now, there are various arguments why this psi has to be quantized. More in general, you can think of this as a charge, and one of the standard law of quantum gravity is that charge is quantized. So this one assumption you will need, but not much more than this, because once you assume that psi is quantized, essentially you don't have any freedom in tuning it to be arbitrarily small. So if you want to make this cosmological constant small, the only option is that you have to tune the gauge coupling to be small. So if you are interested in this limit, you are going essentially towards a limit of small gauge coupling, so towards a limit of restoration of a global symmetry, which in this case is U1 R symmetry. And this is telling us that something is bad, probably in this direction. still, you might say that I'm not forced to look into this limit. I can just study the model away from this limit, and nothing is bad in that case. To say that indeed the model is bad always, you can use the weak gravity conjecture, because the weak gravity conjecture allows you to trade the gauge coupling for the cutoff, for the ultraviolet cutoff of whatever is your effective field theory. So you reach a statement that the cosmological constant scale is actually of the same order as the UV cutoff. You cannot decouple them because there is no other parameter you can use to decouple them. Meaning that in this case, you would conclude that this model is not protected against corrections. So this scale is a proxy for the IR cutoff in the sitter. So you are in a situation in which IR cutoff and UV cutoff are not decoupled, so there is no window really in which your effective field theory can live. So this, you would conclude that this is not a good effective field theory, and in general, pure Fayet-Iliopoulos terms are in the swampland. And the same conclusion, in fact, was reached via different argument using absence of global symmetries, but not in this way, in another way, by Komagowski and Seiberg. And what we showed is that the weak gravity conjecture has this information somehow built in. Okay, so this has nothing to do with scale separation, but the point is that you can use it in other models to constrain scale separation in a very similar way. Actually, you can use it in all supergravities, all gauge supergravities with at least 8 supercharges. I will explain why I need 8 supercharges at least. And you can show that this relation parametrically cannot be satisfied. So this would be parametric scale separation. I cannot exclude to have a small amount of scale separation depending on what is small, but parametrically I can exclude this relation if the weak gravity conjecture holds. This completely general will not use assumptions beside the weak gravity conjecture here. You can do a similar work for the sitter, but I need one more assumption for the sitter. It's not automatic. And of course, as I was saying, there is one assumption underlying all of this, which is the fact that the weak gravity conjecture holds in ante the sitter or the sitter, so away from Minkowski where it is originally formulated. And it holds in such a way that this relation is not modified drastically. So there can be corrections, which, for example, can be small when the radius of your space is, of your ADS space is large. Of course, this is an open problem which I'm not going to solve. What is the correct formulation of the weak gravity conjecture away from Minkowski I think is not known at present. So as a working assumption, I would need to use this slightly away from Minkowski. But still, if we are in the supergravity regime, you expect that corrections suppressed with the ADS radius are small in this case, so you expect that probably this assumption can be meaningful. Okay, so here is a sketch in 2 slides how it works. If you want the precise derivation is a bit more technical, so I didn't put it here, but this is the logic. And I'm doing here in generic notation for any gauge supergravity in 4 and 5 dimensions at least. The starting point is the vacuum energy. And it is a fact that in supergravity, in supersymmetric ante-de sitter vacua, the vacuum energy is always given by the gravitino mass or the trace of the gravitino mass matrix. So here is a completely general fact. Then you need 8 supercharges at least, because with 8 supercharges at least, you can trade the mass here, the gravitino mass, for some function of the gauge coupling. So you go from the gravitino mass sector essentially to the gauge coupling sector. And you cannot do this with 4 supercharges because you have a superpotential, and in general this might not be true for a superpotential from a purely bottom-up perspective. In particular, for n equal to 2, so 8 supercharges in 4 and 5 dimensions, you have to use what is called special geometry or very special geometry, and it's not a big deal to work out the precise relation, and you can show it very explicitly. So you rewrite the vacuum energy in terms of the gauge coupling, but this is a generic gauge coupling of whatever the gauge group is. I'm doing this for any possible gauge group. So in principle, you are almost done, but you have to be a bit more refined in case you want to make sharp statements. So the question is, what is the gauge group? And this can be answered, actually. What is the form of the gauge group in the vacuum for supersymmetric ante-de sitter vacua is known, and at least is known for the part we are interested in. So it is known that whatever the gauge group is, it breaks into 2 pieces. One piece is gauged by what is called the graviphoton, and another piece is this piece will be gauged by the other vector fields in the theory and is model dependent. However, this piece gauged by the graviphoton, the graviphoton is always there with at least 8 superchargers, is model independent and it can be calculated. The generic form is this one. So if, for example, for n equal to 2, you will see that there is always a U1 factor. Otherwise, the group is bigger, but you can either argue with the Cartan subalgebra or assume that there is an unbroken U1 factor, which is typically the case if you look at the concrete models. So once you have understood the structure of the gauge group, you can just split the contribution into the graviphoton contribution plus whatever else is remaining, the matter contribution. Due to the properties of supersymmetry, there is really a plus sign here, so you can neglect this part, and you have an inequality of this kind. You take the absolute value and you impose the weak gravity conjecture, and essentially you derive the relation that the Hubble scale or the cosmological constant scale cannot be decoupled by from the UV cutoff. The reason is that whatever is here is a gauge coupling, is a whole thing which is a gauge coupling. You don't have any other parameter outside this function. So there is no other field or parameter here which I can tune. It's really a one-to-one relation between these two scales. And this then, from this you can conclude that if you believe the weak gravity conjecture in this way, there is no scale separation for this model. So let me give you an example very briefly. A known class of models from top down, which gives for the n equal to 2 gauge supergravity, is M theory on Sasaki-Einstein 7 manifold. To specify the theory, you have to tell me the pre-potential, which is a function of the scalar field here, and also the quaternionic metric, which is needed to understand the gauge sector, the gauging. You can understand that there is a U1 cross U1 gauging, which breaks down to U1 on the vacuum. So there is a U1 on the vacuum as expected. And you can work it out very explicitly. You can understand what are the moment maps of this U1. You will have a Heliopolos gauging. And you can calculate the vacuum energy. You will see that indeed it is given by the product of the gauge coupling and the charge and the number. There is no other parameter entering this relation. So Q cannot be tuned small because it's a charge. And then the only way to have small and then you essentially G is the UV cutoff, so you cannot decouple again the UV cutoff from the cosmological constant. So what you would conclude is that these models are honest model in string compactifications, but they are not good four-dimensional effective field theories. If you want to use them as four-dimensional effective field theories, you are in clash with the weak gravity conjecture. So the results we have is that we have an explicit argument for n equal to 2 and n equal to a supergravity in 4 and 5 dimensions. And we believe that there is no clear obstruction in going beyond. In particular, we don't see any clear obstruction in proving it for any number of supercharges in the between, and also in going beyond 5 dimensions. In fact, there are even proof in step 2, for example, that supersymmetric anti-de Sitter 7 vacua cannot be scale separated. You can be a bit more brave. You can combine this with other conjectures. For example, those saying that non-supersymmetric anti-de Sitter vacua are unstable. And this would probably tell us that there are no really lower dimensional effective field theories in anti-de Sitter regardless of supersymmetry, but these are yet a further step. So what we learn from this is that the room, the only window which is still not covered, so where scale separation seems to be possible with respect to this logic, is the case in which we have only 4 or less supercharges, meaning 4d n equal to 1 or, for example, 3d n equal to 2 or less. And indeed, all known examples in the literature, in string compactifications, are in this window. There are no other examples known, as far as I'm aware, in other regions. So before going into one of those examples, let me briefly tell you how you can modify this to say something for the Sitter. The starting point is always the vacuum energy, which now, however, has 2 contributions. One entering with a plus sign, which is breaking supersymmetry, and the other with a minus sign. Due to this fact that there is this minus sign, in principle, I can tune this scale to be small by cancelling one contribution against the other. So this is the way out for the argument I just gave you. And the only way to proceed that we saw is that we had to assume that the gravitational mass is vanishing. So what we can say is that for the Sitter vacuum with vanishing gravitational mass, you just have the gauge coupling here, then you repeat the same trick. You identify a factor of the gauge group, which you associate to the weak gravity conjecture, and then there is the rest. And then you play exactly the same algebra to derive the bound I showed at the beginning. So the IR cutoff is essentially of the same order as the UV cutoff. So these models are not protected against correction. So you might say that this assumption about vanishing gravitational mass is a bit exotic, but this is not, at least not in the supergravity literature. All the few known stable de Sitter vacua in n equal to 2 or bigger than 2 supergravity in 4 dimensions have this property. So in 4 dimensions we could rule out all non-stable vacua just in supergravity. In 5 dimensions, to our surprise, when we look into the literature, there are vacua which are stable, the Sitter 5 vacua just in supergravity, but don't have this property. So still, I think this is an interesting direction to be understood further, because for some reason you would expect that this model, by a dimensional reduction, will go down to this model, but it's not so straightforward. They seem to have different properties with respect to the weak gravity conjecture. And this is interesting to be investigated further also in light of this recent work connecting higher dimensional de Sitter to lower dimensional cosmic acceleration. Anyway, the message for de Sitter is that modulo the assumption on the gravitational mass, the most promising corner seems to be again a corner with very few supercharges at the Lagrangian level. And finally, before going to the top-down construction, what I showed you can be perhaps a hint of a more general lesson, which is the fact that somehow Swampland conjecture have a nice behavior. Yes? First derivative equal to 0. I'm not checking stability. No. I think there are examples, yes, but those are tachyonic, so we are mainly aiming at stable vacua. But I think there are also examples. I have to check again because it was 1 year ago. I don't remember the literature, but I think there are examples with 0 gravitational mass and the tachyonic direction. Yes, I can tell you later. I just have to check. Okay. No other questions? No. Okay. So I was saying that this perhaps is hinting at a more general picture that supergravity combined with Swampland conjecture is a useful tool in the sense that I showed you instances of this first line here. So supergravity plus weak gravity is essentially giving us statements which are the manifold of supergravity plus de Sitter conjecture. So I was excluding de Sitter vacua using another Swampland conjecture. And perhaps you can be a bit more brave and start from a known conjecture and try to predict a new one. Of course, this is much more challenging also if you really work just at the supergravity level, but this is an open possibility. Now, the second part, and in what is left, I will review a construction of a scale-separated class of vacua in type 2A, which was already mentioned this morning, but I will focus on some specific properties. Now, as we know, one of the most celebrated class of vacua is what is called DGKT after the authors of this paper, even though many of this paper here, but many other people contributed to it during the years. And this model has some peculiar properties. So it is a massive type 2A compactification on manifold with SU3 structure, and those explains singularities. And there is a nice property, which is the fact that you have a parameter, a flux parameter, for flux in this case, which is not bounded, is not entering Bianchi identities, it can be arbitrarily large. This is a nice property per se, but what is remarkable about this class of models is that when this parameter is large, other remarkable things are happening. So the cosmological constant becomes small in magnitude, so you are going towards Minkowski essentially, and you are going in a regime of large internal volume and small string coupling. So you are more and more in a regime in which you can trust your supergravity computation. Of course, there are reasons of concerns which we have heard about this morning. One is that these are vacua in massive type 2A, which are somehow more difficult to understand geometrically from 11D perspective. And also, as Thomas was saying, you are in a situation, you find the solution in an approximation. So you don't find straight ahead the full solution, you find an approximated solution, which is called a smeared solution. And recently, it has been understood how to make progress along this direction. So in fact, both concerns can be addressed. This was one of the motivation of our work. The first concern was already somehow addressed in this paper. The idea was presented here, essentially is to go to massless type 2A by appropriately choosing T-dualities. The second concern is the possible solution to the second concern is instead more recent, is due to these people. And the idea is that you can set up, in this case, it's not always true, but in this case you can set up a systematic expansion because there is a parameter which is naturally small, which is again a power of this flux number. And then you just solve equations systematically, order by order, in this perturbation theory. So you can capture order by order, in principle, the correction to the smeared approximation. And what people did so far, indeed, is just the first order because the computation is demanding. But in principle, the tools are there. So we combined these two steps, and this led us to possible evidence for scale-separated vacua in massless type 2A. It actually both have weak and strong coupling, meaning that also this vacua could be also vacua in empty. The setup is the following. You have what is called the Nivasawa manifold, which is essentially a special subcase of a twisted torus. And what is important that I'm going to stress less is that you can think of this T6 as 3 copies of two torus, so we have 3 two tori. And the general solution was, smeared solution was already known. We computed the first order correction in the back reaction to this solution. But before doing so, we actually perform a generic scaling analysis. So we ask ourselves which scaling freedom we have in the parameters, in the size of this tori to play with. And this turned out to be crucial for this model because, first of all, a fairly general scaling class is this one. There are 3 parameters, A, B, C, which are arbitrary, modulo some conditions for consistency, but they are basically arbitrary. And then once you are here, you can just tune your A and B, C and ask for your favorite properties. You can tune A, B, C and ask for scale separation. And if you do it, you will see that if you insist on an isotropic manifold, so all radii to be equal, you don't find scale separation. So if you would have naively started from an isotropic case, without performing the scaling analysis, you would have concluded that this class of vacua has no scale separation. You have missed this possibility. Instead, you can choose the 3 two tori to be different. So what we choose is in fact this situation. The second torus is bigger, then the third one is intermediate, and then the first one is smaller. But they are all growing with n. Nothing is shrinking. Scale separation is controlled by one of these parameters, and indeed you can have arbitrarily, parametrically scale separation at both weak and strong coupling because you can tune the other parameters here. Now here I have a comment on the flip, but I think I will skip for reasons of time. Let me conclude. So scale separation, I think, is a meaningful property to demand for string compactification or for string phenomenology. It's not the only way to go, but is a meaningful way at least. It's a meaningful assumption. And we gave evidence just purely from supergravity that vacua, scale separated vacua, if they exist, probably they are in a region with few supercharges, or something is going on with the weak gravity conjecture that we still have to understand in anti-de Sitter space. And for the second part, I think one of the lessons you can draw from these works is that probably there are more solutions we are not aware of with scale separation, at least at the supergravity level, so even the smeared level. But you have to ask for non-isotropic cases. Indeed, very recently there is a series of work going in this direction, and I think that is a very promising direction to research. So, thank you.
Thank you for a very nice talk, Niccolò. Many questions.
Can you quickly comment on the uplift?
Okay, here I just have one slide. I mean, there are many more things to be said, but just what I wanted to, one property that we understood here is that if you try to uplift directly the smeared solution, it doesn't work because the smeared solution has a negative R7 curvature, while if you solve the equation of motion in 11D, you find positive, I mean, as Thomas was saying. And the mismatch can be explained, we explain the mismatch really with computing the correction in the back reaction. So the correction were precisely the right amount to flip the sign. So this non-trivial consistency check. It doesn't prove that it exists in general, but it's a first consistency check which could have failed, and it didn't at this level.
Thanks a lot. Thanks for the talk.
Yeah.
Yeah, how do you resolve in 11 dimensions the O6?
We don't
Like you said.
flat space is this teaching magic. In this case, we don't know. We have a classically singular geometry. I mean,
It is related to some twisting of the tori?
in which sense do you mean?
Well, if you do T-duality, you go to 8 dimensions, then you go back in 11 and Roma's mass exchange with some twisting parameter of the two flux.
Okay, I'm not sure. I'm not sure. And I think the most basic answer is that we don't know. We have a classical singular geometry. That's it.
Okay. Thanks.
One more here.
Thanks for the talk. Very naive question, maybe I just missed it. In the case of the de Sitter, are you able to rule out the existence of the vacuum, or just to show that it's numerically separated?
No, I'm ruling out effective field theory. So the vacuum is there, but it's not protected against corrections. Because I can, if the gravitational mass is vanishing, you, yes. You find that the cosmological constant of your vacuum is given precisely by the gauge count in your game.
That's the same thing we had in ADS, right?
Yes.
Okay.
Precisely. Is the same argument with one more assumption here.
Okay.
Question? Go on, throw it.
Okay.
You can throw it.
Thanks. One sort of possibility that was not in your list in the ADS case was 6 supercharges in 3D. Is there anything to say about that?
6 supercharges. No, I didn't look at that, so I don't know. I don't know even if there are vacuum. I just really don't know.
Okay.
Do you know if there are?
There are Minkowski vacuum.
Yes.
No. I mean, ADS, I don't know.
Okay.
Yeah.
I mean, Minkowski is a bit.
Yeah.
In case of Minkowski for space separation is a bit.
Yeah, of course. No, so I don't know if there are ADS vacuum, but it's just in the numerology.
No,
Be
yes.
interesting. Yeah. Okay. Thanks.
One last question. Yeah.
Thanks a lot for the very nice talk. When you find those ADS vacuum in type 2A, how large are the flux quanta? Like, are they really big, or are they...
Sorry?
How large are the flux...
Big again. You can put as large as you like. It's exactly the same.
Oh, I see. So your flux quanta are not constrained by the Tepel cancellation condition?
There is one flux quantum which is not constrained, which is playing exactly the same role as Michigit is. 6 flux in this case, while Michigit is 4 flux.
Okay, let's thank Niccolò again for the very nice.